there, this is Christy. Today I'm going to show something fun involving a clash of art and math, which I call them fractals and fractal dimensions. The fun here is that we're going to become amateur cartographers or topologists by exploring the numeric world of dimensions using maps. So, are you ready? First, to familiarize with what a fractal is, it is a mathematical set of patterns that are under self-similarity. To briefly point out its history, the term is originated from the Latin word fractus, which means broken. French mathematician Benoit Mandelbrot discovered this in 1975 and had initially used for urban planning. The examples of fractals are quite ubiquitous. The most common ones are ferns. To take a further step, a fractal dimension is what is measured to know the extent of complexity of its patterns. Here the ratio, represented as a small case r, and the number of divided pieces, referred to as n, are the factors needed to be considered to calculate the dimensions d. Here, see the diagrams shown. Starting from the leftmost, the red diagrams. I'll make a t-chart that demonstrates the relationship between r and n. Now, do you see something? A simple and a familiar looking relationship? Yeah, the reciprocal of r equals n. So if we substitute one of the number pairs into the previously introduced relationship, we will get a d value of 1, meaning that the dimension of the red line is 1. When we complete the t-chart for r and n, this time when r is 1/2, the pieces increase from what we had with rare figures. If you take a close look at the overall relationship, the reciprocal of 1/2 to the dth power equals 4. I mean, that's 2 to the dth power equals 4. And, well, we see that d is 2. I mean, it tells that the blue figures are two-dimensional figures. The same works for the green cube. When we substitute r equals 1/2 into the equation, we will probably get 2 to the dth power equals 8. This means that the figure are three-dimensional. Now we're pretty sure what the fractal dimensions deal is about. Now let's give it a go and start a question. Here's a map of Britain. Its coastlines were measured with 3 different standard lengths. Using these, we'll estimate the map's dimension and evaluate the accuracy of the measurements. I mean, these are really the jobs that topologists and cartographers do. So, here we go. First of all, do you notice something? Yep. As standard lengths of measurements decrease, the higher the accuracy of the coastline measurements and the longer the total perimeter become. Let's first create a t-chart to organize the data. Try to change the variables into r and n. We can set a ratio using the longest and the shortest standard values of measurements, and probably both L and G values to get the n values. So applying the fractal dimension relationship, we substitute 1 over r for g over g naught, and probably n for L over g. We can get a formula of r equals g naught to the dth power times g to the 1 minus dth power. See, if we put both logarithms on both sides, what do we get? A y equals ax plus b formula. Nice. Now all we need to find is the value that equals to 1 minus d. Again, a reminder, we're trying to estimate the d value here. So we're going to use the calculator's help to get the linear regression of the relationship. Okay, here. Got an equation that says y equals negative 0.27x plus 9.19. We finally get a d value of 1.27. I find the nature of math undeniably attractable, and that it is always applicable to our reality. I hope the DIS students always have fun learning math and never feel frustrated with learning them. So that was my last project for DIS on fractals and fractal dimensions, and I hope you had fun watching it. Thank you.